On July 12, 2022, NASA released the first operational images from the James Webb Space Telescope. The telescope, a project decades in the making, had traveled 1 million miles from Earth and unfolded its gold-plated mirrors, cooling to a temperature just a few degrees above absolute zero. Its purpose was simple but profound: to see what had never been seen. One image, called Webb's First Deep Field, showed a tiny patch of sky, an area that would be covered by a grain of sand held at arm's length. Yet within that speck were thousands of galaxies. Some of them appeared red and distorted, their light stretched by the expansion of the universe over billions of years. The light from the most distant of these galaxies had been traveling for over 13 billion years to reach the telescope's sensors. The GEOST was not just a telescope, it was a time machine. It was built on a fundamental principle of our universe: light, for all its incredible speed, is not instantaneous. The 186,282 miles it covers every second is a finite number. This means that looking out into space is the same as looking back in time. The sun we see in the sky is always 8 minutes in the past. The nearest star system, Alpha Centauri, is over 4 years in the past. The light from the Andromeda Galaxy began its journey 2.5 million years ago, long before modern humans existed. We live in a universe of delay, a place where the present is a patchwork of different pasts. But what if that delay was not measured in years or minutes, but in seconds right here in our own rooms? What if the speed of light was not 186,282 miles per second, but something drastically noticeably slower? The consequences would reach into every corner of existence, from the structure of atoms to the way we have a simple conversation. The universe would not be the same. We would not be the same. Number 20, our basic perception of reality would fracture. Human reaction time to a visual stimulus is, on average, about 250 milliseconds, or a quarter of a second. The electrochemical signals that travel from your eye to your brain and then to your muscles take time. This is a biological speed limit. The fastest a human has ever been recorded reacting to a starting gun is around 100 milliseconds. But in our world, the speed of light is essentially infinite for everyday distances. The time it takes for light to travel from a lamp to your eye across a room is about 10 nanoseconds. This is so fast that it plays no role in our perception. Our reality is coherent. What we see, what we hear, and what we touch are all synchronized. If the speed of light were, for example, 30 miles per hour, about the speed of a car in a city, this coherence would shatter. The world would become a place of constant, maddening delay. You would flip a light switch, and the room would remain dark for a noticeable fraction of a second as the light struggled to travel from the bulb to your eyes. If the bulb was 15 feet away, it would take about a third of a second for you to see it turn on. Your brain, accustomed to instant feedback, would be in a state of perpetual confusion. This lag would create a fundamental disconnect between your actions and their perceived consequences. Clap your hands in front of your face. You feel the impact and hear the sound almost instantly, but you would see your hands meet a moment later. This delay would permeate every interaction with the world. You would push a door open and feel the resistance of the wood long before you saw the door actually move. You would, drop a glass, hear it shatter on the floor, and then a moment later see the visual of the event. This constant temporal dissonance would make simple tasks difficult and frustrating. Think about trying to catch a ball. Your brain calculates trajectory based on a constant stream of visual information. But if that information is always out of date, your calculations will always be wrong. You would always be reaching for where the ball was, not where it is. This fracturing of perception would also affect our sense of a shared reality. Two people in the same room would experience events at slightly different times, depending on their distance from the event. The person closer to the shattering glass sees it shatter first. The person farther away sees it a moment later. We take for granted that no is the same for everyone in a room. In a slow light world, no would be a private, localized phenomenon. The very foundation of a shared objective present moment would crumble, replaced by a million slightly different pasts all happening at once. Number 19 conversation would become a staggered mess. In our universe, the speed of sound is vastly slower than the speed of light. Sound travels through air at about 767 miles per hour. Air light travels at about 671 million miles per hour. This is why you see lightning before you hear thunder. The visual information reaches you almost instantly, while the sound information lags behind. It's a simple rule we all learn. During a conversation with someone a few feet away, this difference is negligible for both light and sound. The delay is in microseconds. Now, let's set the speed of light to be much slower, say 100 miles per hour. The speed of sound remains 767 miles per hour. The old rule would be inverted. You would hear things before you saw them. Imagine a conversation with a friend standing 20 feet away. Your friend speaks. The sound of their voice, traveling at 767 mph, reaches your ears in about 18 milliseconds. That's practically instantaneous for human perception, but the light from their face, from their moving lips, travels at only 100 mph. It would take about 136 milliseconds to reach your eyes. This is a noticeable delay. You would hear your friend's entire sentence, and then a moment later you would see their lips move to form the words you just heard. It would be like watching a badly dubbed movie, but in real life all the time. The natural rhythm of conversation would be destroyed. We rely on a constant stream of non-verbal cues, a raised eyebrow, a slight smile, a nod of the head step, to understand the full meaning of what is being said. These cues would now arrive late, desynchronized from the words they are meant to accompany. Someone could tell a joke, you'd hear the punchline, and you might start to laugh before you even saw the smile on their face. You might ask a serious question and see their somber expression form only after you've already heard their reassuring reply, creating a moment of emotional whiplash. The subtle, intricate dance of human interaction would become a clumsy, staggered march. This effect would become more pronounced with distance. Trying to talk to someone at the other end of a long hall would be a lesson in frustration. Shouting across a field would be almost impossible to do coherently. You'd hear their reply long before you saw any indication that they had even heard you in the first place. Video conferencing, a staple of modern life, would be a bizarre experience. The audio would be clear, but the video would lag so severely that the person on screen would be reacting to things you said several seconds or even minutes ago. Human connection, so dependent on shared moments, would be frayed by the simple, inescapable lag of light. Number 18, the Doppler effect would paint the world in shifting colors. The Doppler effect is the change in frequency of a wave in relation to an observer who is moving relative to the wave source. We experience it most often with sound. When an ambulance approaches, its siren sounds higher in pitch because the sound waves are compressed. As it passes and moves away, the siren sounds lower in pitch because the waves are stretched out. The same exact principle applies to light. When a light source moves towards you, its light waves are compressed, shifting them towards the blue end of the spectrum, a blue shift. When it moves away, the waves are stretched, shifting them towards the red end, a red shift. In our universe, the speed of light is so immense that you need to be moving at incredible speeds for this effect to be visible to the naked eye. Astronomers use it constantly. The redshift of distant galaxies discovered by Edwin Hubble in the 1920s was the first piece of evidence that the universe is expanding. But in our daily lives, it's completely unnoticeable. A car speeding past at 70 mph experiences a minuscule Doppler shift that is detectable only by sensitive instruments. If the speed of light were much slower, say 200 miles per hour, the visual Doppler effect would become a spectacular and constant feature of everyday life. The world would be painted in shifting colors based on motion. An object's color would no longer be a stable property, but a function of its velocity relative to you. Imagine standing on a sidewalk. A person riding a bicycle towards you at 15 mph would appear distinctly bluish. Their red jacket would look purplish. Their skin would take on a cool blue tint. As they passed you and began to move away, their color would dramatically shift. The blue tint would vanish, replaced by a warm reddish glow. Their jacket would now look deep orange, and their skin would appear ruddy. Cars would be even more dramatic. A car approaching at 40 mph would be intensely blue. A car speeding away would be a fiery red. A busy street would be a constantly shifting kaleidoscope of blues and reds, a visual representation of the flow of traffic. Looking at your own hand, it would be its normal color. But if you moved it quickly towards your face, it would flash with a hint of blue. Waving goodbye to someone, your retreating hand would appear reddish. This would have profound effects. Traffic lights would be a challenge. Is that light truly red, meaning stop, or is it a green light that is moving away from you so fast that it has red shifted into the red part of the spectrum? Is an approaching blue light a police car, or just a normal car that happens to be coming towards you? Colors would lose their objective meaning, becoming slippery relational properties. Our language for color, built on the assumption of stability, would have to adapt to a world where a reed ball is only red when it's standing still. Number 17, mirrors would show you the past. The Hall of Mirrors at the Palace of Versailles, completed in 1684, contains 357 mirrors. When you stand inside it, you see an almost infinite series of reflections. The light from your body travels to one mirror, reflects to another, and back to your eye. In our world, this journey is so fast it feels instantaneous, like the delay is on the order of nanoseconds. The person you see in the mirror is, for all practical purposes, you in the present moment. Let's slow the speed of light down to something human scale, like 10 feet per second. This is a brisk walking pace. In this world, mirrors would become portals not to another place, but to another time, the immediate past. Stand 5 feet from a mirror. The light from your face must travel 5 feet to the mirror and 5 feet back to your eye. That's a total of 10 feet. At a speed of 10 feet per second, this journey would take exactly 1 second. When you look in the mirror, you would not see yourself as you are now. You would see yourself as you were 1 second ago. This would be deeply unsettling. You could raise your hand, and for a full second, your reflection would remain still. Then you would see the reflection of your hand rise, a ghostly echo of an action you have already completed. You could smile and then watch your own past self smile back at you a second later. The immediate intuitive link between action and reflection would be severed. Looking in the mirror would become a conversation with your recent past. This effect would create bizarre paradoxes of perception. You could step away from the mirror and turn your head, and for a moment, you could see the back of your own head in the reflection before it vanishes. It would be possible to see yourself from an angle you normally couldn't, simply by moving faster than the information of your own image. Complex mirror arrangements like those in a tailor's shop or a funhouse would become temporal labyrinths. Each reflection would represent a different point in the past. The first reflection would be from 1 second ago, the reflection within that reflection would be from 2 seconds ago, the next from 3 seconds ago, and so on. You can see a history of your own movements, a series of still frames of your past self, all visible at the same time. The simple act of checking your appearance would become a profound and disorienting experience, a direct confrontation with the fact that even your own image is a relic of a moment that is already gone. Number 16, driving a car would be an act of faith. Modern driving relies on a constant high-speed feedback loop. Your eyes see the position of other cars, the lines on the road, and any potential hazards. Your brain processes this information and directs your hands and feet to make adjustments. This entire loop depends on the visual information being accurate and up to the minute. The time it takes for light to travel from another car to your eye is so small, we treat it as zero. The car is exactly where we see it. Let's reduce the speed of light to 100 miles per hour, a speed easily matched or exceeded on a highway. The world outside your car window would now be a landscape of the past. The positions of all other objects would be out of date. You are driving at 60 mph, another car is 200 feet ahead of you, also traveling at 60 mph in the same direction. The light from that car traveling at 100 points has to cross the 200-foot gap to reach you. This would take about 1.36 seconds. During that 1.36 seconds, the other car has continued to move forward. At 60 mph, it has traveled an additional 120 feet, so the car is not where you see it. Its actual position is 120 feet farther down the road than its visible image. Now imagine a car is coming towards you. Both you and the other driver are going 60 mph. The closing speed is 120 mph. The other car is 200 feet away when the light from it reaches your eye. Again, this takes time. By the time you see it at the 200-foot mark, it has traveled closer. Your brain would be seeing a snapshot of the past while trying to navigate the present. This time lag would make basic maneuvers incredibly dangerous. To change lanes, you would look in your mirror and see the position of a car as it was a second or two ago. You would have to mentally calculate where that car is now before making your move. And a sudden stop by of the car in front of you would be a catastrophe. You would see their brake lights come on, but the light from that event would take time to reach you. The car itself would have been braking for that entire time. Your reaction would be based on dangerously old information. At night, the problem would be even worse. Your headlights would project a pool of light in front of you, but that light would take time to travel to an object like a deer, and then travel back to your eyes. You would outrun your own vision. By the time you saw the deer, you might have already hit it. Driving would no longer be a reactive skill. It would become a predictive one, a constant series of gambles based on a blurry, time-delayed picture of the world. Your highway safety would depend not on reflexes, but on complex mental arithmetic. Number 15 sports would be unplayable. The physics of a baseball game are a marvel of high-speed action. A major league pitcher can throw a fastball at 100 miles per hour. The distance from the pitcher's mound to home plate is 60 feet, 6 inches. The ball covers this distance in about 400 milliseconds. A batter has less than half a second to see the pitch, judge its trajectory, and swing. This is already at the very limit of human reaction time. This whole process works because the visual information from the ball travels to the batter's eye almost instantaneous. If the speed of light were, say, 200 miles per hour, this delicate timing would be completely destroyed. The baseball itself would be traveling at half the speed of light. The pitcher releases the ball. The light from that moment begins its journey to the batter's eyes. The ball also begins its journey. But the light is only twice as fast as the ball. By the time the batter sees the ball leave the pitcher's hand, the ball itself has already traveled half the distance to the plate. The batter would see a ghostly image of the ball back at the mound, while the real invisible ball is already 30 feet away and closing fast. It would be impossible to hit the ball. You would be swinging at a memory. The location where you see the ball is a place it has long since abandoned. You would have to guess where the ball is going to be and swing in advance, a pure act of faith. This would apply to every sport. In soccer, a player kicking the ball would see the ball connect with their foot a moment after they felt the impact. The goalkeepers would have to dive to block a shot based on where they think the ball will be, as the visual of the kicked ball would be a trailing indicator. In tennis, a 120 mph serve would mean the player would see the ball leave the opponent's racket when the real ball is already halfway to their side of the court. Even something as simple as a game of catch would be a comedy of errors. You would toss the ball to a friend. They would see it leave your hand, but by then the ball would be much closer to them. Their hands would go to the wrong spot. The game would require both people to ignore what they are seeing and rely on an internal sense of timing and prediction. Sports, which are a celebration of physical reaction and coordination, would become exercises in abstract mental calculation, played against the ghost images of a world that is always one step ahead. Number 14, photography would capture smeared time. A camera works by opening a shutter for a fraction of a second, allowing light from a scene to fall onto a sensor or film. This process captures a single, frozen moment in time. The assumption is that all the light from that scene, whether it's from a person's face or the mountain behind them, arrives at the camera at effectively the same time. This is what creates a coherent, sharp image. The invention of photography, with the first permanent photo created by Joseph Nicephore Niepce around 1826, was about capturing an instant. If the speed of light were dramatically slower, a photograph would no longer capture a single instant. It would capture a slice of time with different parts of the image corresponding to different moments. This is related to an effect in modern digital cameras known as rolling shutter. In a rolling shutter, the sensor is read line by line, from top to bottom. If something moves quickly across the frame, it will be in a different position when the bottom of the sensor is read than when the top was read, leading to skewed or warped images. With a slow speed of light, this effect would be inherent to the physics of light itself, not the technology of the camera. Imagine taking a picture of a car moving from left to right across your field of view. The light from the front of the car has a slightly shorter path to the camera lens than the light from the back of the car. In our world, this difference is irrelevant, but in a slow light world, it would be significant. The light from the front of the car would arrive first, followed by the light from the middle, and then the light from the back. If the car is moving, this means the camera would capture the front of the car at one point in time t1, and the back of the car at a slightly later point in time t2. But during the interval between t1 and t2, the car has moved forward. The resulting photograph would show a car that is stretched out and distorted, looking longer than it actually is. Conversely, a car moving towards the camera would appear compressed. The light from the front of the car has a longer journey than the light from the back, but because the car is moving towards the camera, it shortens that journey. The visual effect would be to squash the car, making it look shorter. Photography would cease to be a tool for accurately representing reality. It would become a form of art that captures the strange relativistic distortions of a slow light world. A portrait would be a challenge. If the person moved their head even slightly during the exposure, their face would be warped. For landscape, photography would be the only genre to remain relatively unchanged, as long as nothing in the landscape was moving very fast. The camera, invented to freeze a moment, would instead reveal the inescapable flow and distortion of time. Number 13, the internet, would grind to a halt. The modern internet is built on speed. Data is transmitted across the globe through a vast network of fiber optic cables laid on the ocean floor. The first transatlantic telecommunications cable, TAT-1, was laid in 1956 and could handle just 36 phone calls. Today's cables can carry terabits of data per second. This data, encoded in pulses of light, travels through the glass fibers at roughly 2/3 the speed of light in a vacuum. This is incredibly fast. A signal can travel from New York to London and back, a round-trip ping, in about 70 milliseconds. This speed is not a luxury, it's a necessity. High-frequency financial trading depends on executing trades milliseconds faster than competitors. Video calls rely on low latency to feel natural. Cloud computing requires fast access to data stored in servers thousands of miles away. If the speed of light were drastically slower, say 1,000 miles per second, the entire architecture of global communication would collapse. Let's recalculate that New York to London ping. The distance is roughly 3,500 miles. At 1,000 miles per second, a one-way trip would take 3.5 seconds. A round trip would take 7 seconds. It's a 7,000 millisecond ping, up from 70. A simple Google search would take many seconds just for the signal to travel to the server and back, not including any processing time. A video call would be impossible. You would say something and the person on the other end wouldn't hear it for several seconds. Their reply would take just as long to come back. The conversation would be a series of long, awkward pauses. It would be less like a call and more like exchanging a series of very slow voice messages. Trying to use a website hosted on another continent would be an exercise in extreme patience. Each click, each image load, each piece of data would require a multi-second round trip. Websites that are now rich with interactive content would have to be stripped down to plain text, reminiscent of the internet of the early 1990s. The global economy would fragment. Financial markets, which are now interconnected and operate 24/7, would be unable to function. A price change on the Tokyo Stock Exchange would take seconds or minutes to be known in New York, an eternity in the world of finance. This information asymmetry would make global trading impossible. The internet has connected the world by making distance almost irrelevant. A slow speed of light would reintroduce that distance with a vengeance. The world would feel vast and disconnected again. Communication would become local. Your digital life would be confined to servers in your own city or region. The global village would crumble into isolated electronic towns. Number 12, your computer would be slower than an abacus. The clock speed of a computer's central processing unit CPU is a measure of how many cycles it can perform per second. A modern CPU might have a clock speed of 4 GHz, meaning it performs 4 billion cycles per second. In each one of these incredibly brief cycles, an electrical signal has to travel from one part of the chip to another. The ultimate speed limit for these signals is the speed of light. A CPU chip is tiny, perhaps half an inch across. But even across this small distance, the speed of light is a limiting factor. At 4 GHz, one clock cycle lasts only 0.25 nanoseconds. In that time, light in a vacuum travels about 3 inches. Because signals in copper wires and silicon travel slower than light in a vacuum, the maximum distance a signal can reliably travel in one clock cycle is only a few centimeters. This physical limit is one of the reasons why simply making chips bigger doesn't make them faster, and why engineers have moved to multi-core designs. Now, let's dramatically slow the speed of light to, for example, 100 meters per second. This is the speed of a world-class sprinter. On a computer chip that is 1 centimeter 0.01 meters across, it would now take a signal 0.0001 seconds to travel from one side to the other. This means the absolute maximum number of cycles the CPU could perform is the inverse of this time, which is 10,000 cycles per second, or 10 kilohertz kHz. Not gigahertz, not megahertz, but kilohertz. A computer with a 10 kHz processor would be unimaginably slow. The second computer, released in 1977, had a processor that ran at 1 megahertz, which is 100 times faster than our hypothetical slow-light computer. Your powerful modern smartphone would have less processing power than a pocket calculator from the 1980s. Loading an operating system would take days, if it could load at all. Opening a simple text document would be a lengthy process. Rendering a single frame of a video would take hours. The digital revolution, which is built on the foundation of exponential growth in computing power described by Moore's law, would never have happened. All electronics would be affected. The signals inside your phone, your television, your car's engine control unit, all of them would be constrained by this new, sluggish, universal speed limit. We would be stuck in a permanent electronic dark age. The intricate, high-speed choreography of electrons that powers our modern world would slow to a crawl, and the society built on that speed would be an impossibility. Number 11, GPS navigation would be impossible. The Global Positioning System, GPS, is a marvel of relativistic physics. A constellation of about 31 satellites orbits the Earth, each one carrying a highly precise atomic clock. These clocks are accurate to within a few nanoseconds per day. Each satellite constantly broadcasts a signal that contains its current position and the precise time the signal was sent. Your GPS receiver on the ground picks up signals from at least 4 of these satellites. By measuring the tiny differences in the arrival time of these signals, your receiver can calculate its distance from each satellite. Once it knows its distance from 4 satellites, it can pinpoint your location on Earth through a process called trilateration. This entire system depends on one thing, the speed of light being a known, enormous, and constant value. The time differences the receiver measures are incredibly small, on the order of billionths of a second. It multiplies this time by the speed of light to get the distance. If the time measurement is off by even a tiny amount, the calculated distance will be off by a lot. An error of just 1 microsecond, a millionth of a second, would result in a position error of 300 meters. If the speed of light were drastically slower, the system would become completely unworkable. Let's use a speed of 10,000 miles per second. The GPS satellites orbit at an altitude of about 12,550 miles. A signal from a satellite directly overhead would now take over a second to reach the ground. 12,550 miles, 10,000 MPs equals 1.255 seconds. The problem is that during that 1.255 seconds, the satellite has moved. The satellites travel at about 8,700 miles per hour, or 2.4 miles per second. So in the time the signal is traveling to you, the satellite has moved about 3 miles. The position information contained in the signal is therefore 3 miles out of date by the time you receive it. Furthermore, your receiver on the ground is also moving as the Earth rotates. The beautiful precision of GPS would be replaced by massive, uncorrectable errors. The system needs to account for both special and general relativity even in our fast light universe. The satellite's clocks run slightly slower than ground clocks due to their high-speed special relativity, but they also run slightly faster because they are in a weaker gravitational field general relativity. The general relativity effect is larger, so the satellite clocks actually gain about 38 microseconds per day relative to Earth. The system is designed to correct for this. In a slow light world, these relativistic effects would be magnified to an absurd degree, making calculations a nightmare. Pinpointing your location to within a few feet would be impossible. Your calculated position could be off by miles, rendering the entire system useless for navigation. Number 10, electricity and magnetism would be unfamiliar forces. In the 1860s, the physicist James Clerk Maxwell brought together the laws of electricity and magnetism into a single, elegant theory described by 4 equations. These equations showed that electricity and magnetism were 2 sides of the same coin. An oscillating electric field creates a magnetic field, and an oscillating magnetic field creates an electric field. This self-perpetuating wave of electromagnetism travels through space. A crucial part of Maxwell's work was calculating the speed of this wave. He found that the speed, which he calls was determined by 2 fundamental constants of nature, the electric constant permittivity of free space and the magnetic constant permeability of free space. When he calculated the value ofs, it turned out to be the same as the measured speed of light. This was a monumental discovery. Light is an electromagnetic wave. The speed of light is not just the speed of light. It is woven into the very fabric of electromagnetism. It is the fundamental speed of causality in the universe. If you change, you are not just changing how fast light travels, you are fundamentally altering the relationship between electricity and magnetism. In a slow light world, this relationship would be different. The strength of the magnetic field produced by an electric current and the strength of the electric field produced by a changing magnetic field would both be altered. This would have profound consequences for all of our technology. Electric motors and generators work by exploiting this relationship. A motor uses an electric current to create a magnetic field that turns a rotor. A generator turns a rotor in a magnetic field to create an electric current. If the link between electricity and magnetism were weaker or different, these devices would be less efficient or might not work at all in the same way. The power grid, which relies on giant generators and transformers which also use electromagnetism, would have to be completely re-engineered. Radio waves, microwaves, and all other forms of electromagnetic radiation would also be different. Their ability to propagate through space would be changed. Antennas would have to be redesigned. The entire field of electronics, which depends on the predictable behavior of electric and magnetic fields in circuits, would be turned upside down. The laws of physics that engineers have relied on for over a century would no longer apply. We would have to rediscover the rules of a new sluggish electromagnetic world. Number 9. The sun's fusion engine would sputter or explode. The sun and every other star is powered by nuclear fusion. In its core, under immense temperature and pressure, hydrogen nuclei are fused together to form helium. This process is governed by one of the most famous equations in physics, E=mc², formulated by Albert Einstein in 1905. It describes the relationship between energy, E, mass m, and the speed of light, c. The equation says that a small amount of mass can be converted into a huge amount of energy because the mass is multiplied by the speed of light squared, which is a colossal number. The sun converts about 600 million tons of hydrogen into helium every second. In this process, about 4 million tons of that matter is converted directly into energy. This is what powers the sun and provides the light and heat that makes life on Earth possible. The sun's stability is a delicate balance. The outward pressure from the energy produced by fusion is perfectly counteracted by the inward pull of its own immense gravity. Let's imagine the speed of light, kig, is dramatically lower. This means chi squared, c squared would be catastrophically smaller. The amount of energy E released from converting a given amount of mass m would be far, far less. If k were 1,000,000 times smaller, then squared would be 1,000,000,000,000 times smaller. The energy output of the sun's fusion reactions would drop by a factor of 1,000,000,000,000. The outward pressure would vanish, and the sun would collapse under its own gravity almost instantly, likely becoming a black hole or a dense, dark cinder. Alternatively, for the sun to produce the same amount of energy it does now to hold off gravity, it would need to convert a vastly greater amount of mass into energy every second. It would have to burn through its hydrogen fuel at an insane rate. Instead of having a lifespan of 10 billion years, its lifespan might be measured in thousands of years, or even less. It would burn incredibly brightly and then quickly die out. In either scenario, life on Earth would be impossible. The stable, long-lived star we depend on could not exist. The very process that powers the universe, the conversion of mass into energy in the heart of stars, is fundamentally dependent on being an enormous value. A slow speed of light would mean a dark, cold, or violently short-lived universe devoid of the stable suns needed to nurture life. Number 8. Matter itself would be less stable. The equation E=mc² doesn't just apply to stars, it governs the stability of matter at the most fundamental level. The nucleus of an atom is made of protons and neutrons, collectively called nucleons. An interesting fact is that the mass of a nucleus is always slightly less than the sum of the masses of the individual protons and neutrons that make it up. For example, a helium-4 nucleus has 2 protons and 2 neutrons. Its mass is slightly less than the mass of 2 free protons and 2 free neutrons added together. This missing mass is called the mass defect. It has been converted into energy, the binding energy of the nucleus, which is what holds the protons and neutrons together against the powerful electrostatic repulsion of the positively charged protons. This binding energy is a direct consequence of E=mc². If the speed of light quake were much smaller, the amount of binding energy released for a given amount of mass defect would be much smaller. This means the force holding atomic nuclei together would be significantly weaker. The consequences would be catastrophic for the structure of matter. With weaker binding energy, complex nuclei would be much less stable or completely impossible to form. The electrostatic repulsion of the protons would overwhelm the weakened strong nuclear force, which is related to binding energy. This means that the periodic table of elements would be much shorter. Perhaps only hydrogen, with its single proton, would be truly stable. Helium might be able to form, but heavier elements like carbon, oxygen, iron, the very elements that we and the world around us are made of, might fall apart. Their nuclei would not have enough binding energy to stay together. The universe would be a far simpler, more boring place. It would be composed almost entirely of hydrogen, with perhaps a little helium. The rich chemistry that leads to planets, stars, and life requires a diverse array of stable elements. These elements are forged in the hearts of stars and in supernova explosions, processes that themselves depend on nuclear physics. With a slow speed of light, this cosmic alchemy would fail. The universe would be a thin, uninteresting soup of the simplest atoms, incapable of forming any complex structures. The very existence of solid matter as we know it would be in jeopardy. Number 7, the periodic table of elements would be radically different. The structure of an atom is defined by two main things: the nucleus at its center and the electrons that orbit it. The behavior of these electrons determines all of chemistry: how they are arranged in shells, how they bond with other atoms, and how they interact with light is governed by the laws of quantum mechanics and electromagnetism. One of the most important numbers in this field is a dimensionless constant called the fine structure constant, represented by the Greek letter alpha A. Its value is approximately 1/137. It characterizes the strength of the electromagnetic interaction. The fine structure constant is not a random number. It is derived from three other fundamental constants: the elementary charge, the charge of a single electron, Planck's constant, and the speed of light. The formula for alpha shows that it is inversely proportional to. This means if the speed of light were to decrease, the fine structure constant would increase. This would have a profound effect on the structure of every atom in the universe. A larger fine structure constant means a stronger electromagnetic force between the nucleus and the electrons. Electrons would be pulled in closer to the nucleus. The size of atoms would shrink. More dramatically, the speed of the innermost electrons would change. In heavy atoms like uranium, the electrons in the lowest orbital are already moving at a significant fraction of the speed of light. If we're lower, these electrons would, according to the standard equations, need to orbit at a speed faster than the new, slower speed of light. This is a physical impossibility. The result is that the periodic table would come to an abrupt end. The calculations show that if the fine structure constant were larger than 1, which corresponds to a speed of light 137 times slower than it is now, the basic quantum mechanical equations that describe atoms would break down. It would be impossible to have a stable atom with a large number of protons. The electromagnetic force would be so strong that it would cause a kind of atomic collapse. This means that a slow light universe would have a much smaller set of possible elements. The periodic table might end at an element like iron or perhaps even carbon. The heavy elements we know, like gold, lead, and uranium, would simply not exist. Their atoms would be fundamentally unstable. The chemical diversity of the universe would be severely curtailed, all because a single universal constant had a different value. Number 6, chemistry as we know it would not exist. All of chemistry is based on the behavior of electrons in atoms. The way atoms bond together to form molecules depends entirely on how their outermost electrons interact. These interactions, gotten covalent bonds where electrons are shared, ionic bonds where electrons are transferred, are all governed by the strength of the electromagnetic force, which is described by the fine structure constant. As we saw, a slower speed of light would mean a larger fine structure constant and a stronger electromagnetic force. This would rewrite all the rules of chemistry. The strength and length of chemical bonds would change. With a stronger attraction between electrons and nuclei, atoms might hold onto their electrons more tightly, making them less willing to form bonds. Or perhaps the bonds they do form would be much shorter and stronger. The very geometry of molecules would be different. The water molecule H2O has its familiar bent shape because of the way the oxygen atom's electrons are arranged. With different electromagnetic rules, that shape could be linear, or the bond angles could be different. This would change the properties of water completely. It might not be a liquid at room temperature. It might not be the universal solvent that is so crucial for life. Carbon's unique ability to form 4 strong bonds and create long, complex chains is the backbone of organic chemistry and life itself. A change in the fundamental forces could alter this ability. Perhaps it could only form two bonds, or its bonds would be too weak to form stable, large molecules like DNA and proteins. The entire basis for life as we know it would be gone. Even the colors of things would change. The color of an object is determined by which wavelengths of light its electrons absorb and reflect. Since the electron energy levels would be different in a slow light universe, the colors of all materials would shift. Or gold might not be yellow, the sky might not be blue, the rates of chemical reactions would also be altered. The energy required to initiate a reaction, the activation energy, would be different. Some reactions that are common in our world might be impossible, while others that are rare might become commonplace. The very concept of a stable compound would have to be re-evaluated. We would be living in an alien chemical landscape where the familiar properties of matter, the hardness of a rock, the wetness of water, the structure of a leaf would be governed by a new and unfamiliar set of rules. Number 5, photosynthesis might be too inefficient for life. Nearly all life on Earth is powered directly or indirectly by photosynthesis. It is the process by which plants, algae, and some bacteria convert light energy from the sun into chemical energy in the form of glucose. This process, which evolved over 3 billion years ago, fundamentally transformed our planet, producing the oxygen in our atmosphere. The first step in photosynthesis involves a pigment, usually chlorophyll, absorbing a photon of light. The energy from this photon excites an electron, initiating a complex chain of reactions. The success of photosynthesis depends on a delicate energy balance. The energy of a photon of light is related to its frequency or color, but the overall energy budget is dictated by the sun's output, which is governed by E=mc². As we've established, a slow light world would likely have a very different kind of star. It would either be much dimmer or much shorter lived. Let's assume a star could exist that provides a similar amount of light as our sun. Chemistry of photosynthesis itself would still be in trouble. The process involves a complex molecular machinery of proteins and pigments, all of which have specific shapes and chemical properties. A slow speed of light would alter the underlying chemistry, changing the shapes and properties of these molecules. The chlorophyll molecule might not have the right structure to efficiently capture photons. The enzymes that facilitate the chemical reactions might not function correctly. Furthermore, the very nature of the light energy might be different in a way that is hard to predict. If the fundamental link between electromagnetism and matter is changed, the way photons interact with electrons in molecules could be altered. The process of converting that light energy into a stable chemical bond might become far less efficient. If photosynthesis were much less efficient, plants would need to be structured very differently, perhaps with massive leaf areas to capture enough energy to survive. It's possible that the energy gain from photosynthesis would be so low that it couldn't support the metabolic needs of a complex organism. Life might be stuck at a simple microbial level, unable to make the evolutionary leap to multicellularity because the basic energy source of the ecosystem is too weak. The green, vibrant biosphere of our planet is a product of a specific set of physical and chemical rules. Change one of the most fundamental of those rules, the speed of light, and that biosphere might never have come to exist. Number 4, special relativity would be part of your morning commute. In 1905, Albert Einstein published his theory of special relativity. It's based on two postulates that the laws of physics are the same for all non-accelerating observers, and that the speed of light in a vacuum is the same for all observers, regardless of their motion. From these simple ideas come some very strange consequences: time dilation, moving clocks tick slower, length contraction, moving objects are shorter in their direction of motion, and the relativity of simultaneity. Two events that are simultaneous for one observer may not be for another. In our world, these effects are only significant at speeds approaching the speed of light. That's why we don't notice them in everyday life. For a commercial jet traveling at 500 mph, the time dilation effect is minuscule, amounting to a few nanoseconds per hour. You need particle accelerators or incredibly precise atomic clocks to measure these effects. But if the speed of light were much slower, let's say 100 miles per hour, relativistic effects would become a part of everyday experience. The Lorentz factor, which determines the magnitude of these effects, would become large at ordinary speeds. Imagine driving your car on the highway at 70 mph. You would be traveling at 70% of the speed of light. The Lorentz factor at this speed would be about 1.4. This means that to an observer standing on the side of the road, your car would appear to be contracted in its direction of motion, looking only about 71% of its normal length. It would look noticeably squashed. Time for you inside the car would be passing slower than for the stationary observer. For every 1.4 minutes that passed for the person on the sidewalk, only 1 minute would pass for you. If you went on a long road trip, you would return home having aged measurably less than the people you left behind. And a career as a truck driver would become a way to extend your lifespan relative to your stationary friends and family. The world seen from your car window would look bizarre. Objects you were approaching would be blue-shifted and distorted. Objects you were moving away from would be red-shifted. The concept of a universal now would be gone. If you tried to synchronize your watch with a stationary clock as you passed it, the process would be fraught with paradox. Relativity would no longer be an abstract theory in a physics textbook. It would be a tangible, visible, and inescapable feature of reality, as mundane and as noticeable as the weather. Number 3, general relativity's effects would be obvious and dangerous. Einstein's theory of general relativity, published in 1915, describes gravity not as a force, but as a curvature of space-time caused by mass and energy. One of its key predictions is that gravity affects not just objects, but light and time itself. We see these effects in our universe. The orbit of Mercury is slightly altered by the curvature of space-time around the sun. Light from distant stars is bent as it passes by massive objects, an effect called gravitational lensing, and time runs slightly slower in stronger gravitational fields. A clock at sea level ticks slower than a clock on a mountain. This effect, though tiny, is real and must be accounted for by the GPS system. The equations of general relativity are linked to the speed of light, c. A smaller value fork would dramatically amplify these gravitational effects, making them far more pronounced in our daily lives. Gravitational time dilation would become a major social issue. Time would pass significantly slower for people living at sea level than for people living in the mountains. A person living their whole life in a coastal city would age noticeably less than a person living in a high-altitude city. A skyscraper would be a time machine. Someone working on the ground floor would age slower than the CEO working in the penthouse suite. This would create a strange new form of social stratification based on altitude. Gravitational lensing would no longer be a subtle astronomical phenomenon. Any massive object, a building, a hill, would visibly bend the light from objects behind it. Looking past the corner of a large building, you might see a distorted, warped image of what is on the other side. The world would have a funhouse mirror quality to it. The most dangerous effect would be near massive objects. The Schwarzschild radius is the radius to which an object must be compressed for it to become a black hole, a region where space-time is so curved that not even light can escape. This radius is proportional to the object's mass and inversely proportional to c squared. A smaller means a much, much larger Schwarzschild radius for a given mass. In our universe, the Earth's Schwarzschild radius is about the size of a marble. To become a black hole, you'd have to crush the entire planet down to that size. But in a slow light world, the Earth's Schwarzschild radius might be measured in meters or even miles. The gravitational effects near the surface of any large object, like a planet or a star, would be extreme. Getting too close could mean being trapped by a steep gravity, well, from which escape is difficult or impossible. Space travel would be incredibly perilous, not just because of the long travel times, but because the universe would be dotted with gravitational traps that are far more powerful than what we experience. Number 2, the night sky would be a chaotic jumble of time. When we look at the night sky, we are looking into the past. The light from Polaris, the North Star, took about 433 years to reach us. The light from the Andromeda Galaxy took 2.5 million years, because the speed of light is so great. All the stars within a single constellation appear to us as they were at roughly the same point in their own history, give or take a few hundred years. This allows us to see patterns, the familiar shapes of Orion or the Big Dipper that are stable over human history. If the speed of light were dramatically slower, the night sky would lose this coherence. It would become a chaotic jumble of different eras, all visible at once. Let's set the speed of light to 1 light year per year, which sounds fast, but is 186,282 times slower than the real value. The nearest star, Proxima Centauri, is 4.2 light years away. We would see it as it was 4.2 years ago. The star Sirius, 8.6 light years away, would be seen as it was 8.6 years ago. The stars of the Big Dipper range from about 60 to 125 light years away. We would be seeing them as they were decades or even a century in the past. More distant stars would be seen from even further back in time. A constellation would no longer be a picture of a single moment. It would be a collage of different time periods. One star in a constellation might be from 50 years ago, the one next to it from 200 years ago. This would be even more dramatic for galaxies. The Andromeda Galaxy is 2.5 million light years away. In this slow light universe, the light from it would take 2.5 million years multiplied by 186,282 to reach us. The universe might not even be old enough for its light to have arrived. We would live in a much smaller, more isolated, cosmic neighborhood. Our view of the universe would be severely limited. We would be able to see only our closest stellar neighbors. The grand, sprawling vista of billions of galaxies that telescopes like the Hubble and JWST have revealed to us would be completely invisible. The sky would be mostly black, punctuated by a few nearby stars. Even those nearby stars would be strange. Because they are moving, their positions in the sky would be a lie. We would see a star at a certain point, but its actual position would be somewhere else, as it would have moved during the years the light was traveling to us. The sky would be a time-delayed illusion, a collection of ghost images whose true sources are elsewhere. Astronomy would be a profoundly difficult science, based on untangling a web of different paths. Number 1, the concept of now would cease to exist. In our daily lives, we operate on the assumption of a universal now. We believe that when it is noon for us, it is simultaneously noon for someone across the street. We feel that events happen at a specific, objective moment in time that is the same for everyone. Einstein's theory of relativity showed that this is technically an illusion. Simultaneity is relative. But because the speed of light is so fast, this illusion is a practically perfect one for all human scales. We can all agree on what is happening now. In a world where the speed of light is drastically slower, this foundational concept of a shared present moment would completely break down. The relativity of simultaneity would become a daily, unavoidable reality. Imagine you are standing in the middle of a very long train car. At the exact same moment, lightning strikes the front and the back of the car. Because you are in the middle, the light from both strikes reaches your eyes at the same time. You conclude, correctly, that the strikes were simultaneous. Now, imagine your friend is standing on the platform as the train speeds past. From their perspective, the train is moving forward. The light from the back of the train has to travel further to reach them than the light from the front of the train. Also, your friend is moving towards the point where the front strike occurred and away from the point where the rear strike occurred. The result is that your friend will see the light from the front strike first and the light from the back strike second. They will conclude, just as correctly from their frame of reference, that the lightning did not strike simultaneously. The front of the train was struck first. Who is right? According to relativity, both of you are. There is no absolute no. Simultaneity depends on your frame of reference. In a slow light world, this wouldn't require a fast-moving train. Two people walking past each other on the street would have different definitions of no. They would disagree on the sequence of events they both witnessed. Did the car's horn honk before or after the light turned green? The answer would depend on how you were moving. This would make society incredibly difficult to organize. How could you have a legal system if two reliable eyewitnesses could have fundamentally different, yet equally valid, accounts of the order of events? How could you coordinate any complex activity, from running a railway to conducting a symphony orchestra, if there was no shared agreement on what was happening at the same time? Our entire sense of a shared reality is built on the idea of a universal clock, a steady, objective passage of time that we all experience together. A slow speed of light would shatter that clock. Each person would carry their own no, a bubble of the present that was slightly different from everyone else's. But reality would become a purely subjective experience. The most fundamental glue holding our world together, the shared moment, would dissolve. We would be left as islands of perception, forever out of sync.